Welcome to lecture number 8. In continuation with the previous lecture, that is basically the DC transient of first order series RL circuit, we have found the different equations for the voltage across the resistance, the voltage across the inductance, and the inductor current, like that. So now if I go for a simulation with the first order series RL circuit, I will find the exactly same result that I have got actually in my previous lecture. Okay. So now just check it. Okay. So this is the circuit of series RL circuit. So here is the DC voltage. It is set as 10 volt. Okay. And this is the resistance, that is 2 ohms, and the inductance is 5 millihenry. And the important point is I set the initial inductor current, that is the 0 ampere, that is before charging the inductor current is set as 0 ampere. Okay. So now if I run the simulation, in the scope we can measure the various parameters. The first one is the DC voltage, second one is the source current, third one is the voltage across resistance, and the last one is voltage across inductance. Okay. So if now run the simulation and check the waveform properly. So this is the simulation waveform. So now the first one is the DC voltage, that is actually the steady state value of the 10 volt. Okay. The second one is the source current. So it is starting from 0 value and it will steady at the final value of 5 ampere. Okay. The steady state value of the current I is equal to V by R. Here V is 10 volt DC voltage and R is 2 ohms. So the current is V by R, simply 5 ampere. Okay. The third one is the voltage across resistance. It is starting from the 0 value and it will steady at the final value of DC voltage, that is the 10 volt. So this is the curve is monotonously increasing. Okay. It is exponentially increasing. Okay, like that. And the last one is the voltage across inductance. It is starting from the final DC value 10 volt and finally it is exponentially decaying and it will steady at 0 value. So these are the 4 graphs that we have already drawn in our previous lecture. Okay. So the interesting thing is the measurement of the time constant. Okay. For first order series RL circuit, the time constant will be L by R. Okay. So here the L is 5 millihenry and R is 2 ohms. So the time constant will be 5 by 2, that is basically 2.5 millisecond. Okay. So that means at the timing of 2.5 millisecond, the inductor current will reach the 63.2% of steady state value. It is basically the proper definition of time constant for first order series RL circuit. So here, look, the steady state value of inductor current, that is the 5 ampere, of which 63.2% means more or less 63.2% of 5 ampere, it is equal to 3.16 ampere. You can check it in your own calculation. So now at 2.5 millisecond we will show that the inductor current at 2.5 millisecond will reach exactly 3.16 ampere. So that is basically the concept of time constant. So here look, this timing, that is 0.005, it is actually 5 millisecond. So we will consider the timing of 2.5 millisecond because it is a time constant. So more or less the half of this portion is 2.5 millisecond. And if I zoom this portion, the second parameter is inductor current. So if I zoom this portion, we will show that here this point is 2.5 millisecond, right, after zooming. So at 2.5 millisecond, the inductor current will exactly crosses the 3 ampere and it is more than 3 ampere. That is almost, we can say, at 2.5 millisecond it is nearly about to 3.16 milliampere. So it is the clear concept of the time constant and it is a nice explanation. Okay. So from here we can easily define the time constant and the other parameter from in our simulation. So this is all about the first order series RL circuit. Okay. So it is very simple. So now we will discuss about the DC transient of the first order series RC circuit. Okay. So now today is lecture number 8. It is lecture number 8. So the name is DC transient analysis of first order series RC circuit. Okay, so this is our today's topic. So first of all, if we draw the circuit diagram, so this will like, suppose this is a DC voltage, right? So this is a switch, and in series one resistance and one capacitance is connected. Okay, very simple. So this is R and this is the C. Okay, so and this is this is V, and I current is flowing from the supply voltage. Now at the switch on condition, suppose the switch is on at t equal to 0, switch is on. That means what is the dynamic equation of the KVL equation in this closed mesh? That is equal to V equal to R into I plus across the C it is 1 by C integration I dt, because the voltage across the capacitance is noted by 1 by C integration I dt. So that means it is basically VR plus VC. That means voltage across resistance and voltage across capacitance, right? So VR means actually the I into R. Okay, so can I write there just R into I is equal to V minus VC? Yes, okay, and then we can write I equal to V minus VC by R. Okay, fine. And from our previous knowledge, it is already known to all of us that the Q equal to I into T. It is basically the charge equation. Q equal to I into T, right? And so from that we can write I equal to dq dt, and again Q equal to C into V. It is already known to us, and then I is equal to d dt of Q, that means dt of C into V. So that means exactly I, suppose it is written as IC, the current flowing through the capacitance, IC equal to C dVC dt. dVC dt means VC means voltage across the capacitance, nothing else. So from that we can write C dVC, that is equal to IC dt. Okay, so that means dVC is equal to 1 by C IC dt. Okay, so if we take the integration, and then we can write VC equal to 1 by C integration IC dt. Here the current IC or IR or total I, it is same because this is a series current. Okay, so now I equal to what? V minus VC by R. Okay, so if I put the value of I, that is very simple, I equal to V minus VC by R. So that is I equal to, and again C dVC dt, that is equal to V minus VC by R. So hence RC dVC dt equal to V minus VC. Okay, so now we can write again dVC minus V minus VC, okay, equal to 1 by RC dt if we integrate the both side, right? So from there we can write minus ln V minus VC, here is the integration constant K, that is equal to T by RC, right? So this is the number one equation. Okay, so now if we put the initial condition, so putting initial condition, that is at t equal to 0, at t equal to 0, that means q equal to also 0. So q equal to again c into v, that c into vc actually. So q equal to c into vc, it is equal to 0. Actually the vc equal to 0, right? So that means from equation number 1, from equation number 1, we can write minus ln v minus 0 plus k equal to 0. Okay, that means k equal to ln v. So this is the basically the initial condition. So now from equation 1, if we put the value of k, and the equation will look like minus ln v minus vc. What is the value of k? That is plus ln v. So that is equal to t by rc. So now it is simply logarithm. That is actually we can write that ln vc minus ln v minus vc, actually it will be v minus vc by v, that is equal to minus t by rc, right? So from that we can write actually v minus vc by v is equal to e to the power minus t by rc. Okay, so we can write 1 minus e to the power minus t by rc, it is equal to vc by v. So from here the final equation of capacitor voltage is v into 1 minus e to the power minus t by rc. So this is the mainly the voltage across the capacitance during the switch on. Okay, so now we can write the capacitor voltage equation in a different way. What is that? Vc equal to v into 1 minus e to the power minus t by tau, where tau equal to rc, it is known as time constant. Okay, so it is basically known as the time constant, tau. So the time constant of a series RC circuit will be R into C, where in case of RL circuit it was L by R. Okay, so now the next equation, that is the voltage across the resistance. So voltage across the resistor, that is equal to VR. So VR equal to I current into R resistance. Okay, so the I equal to VR by R. And what is VR? Is basically simply the difference between V and Vc. So V minus Vc by R. Okay, so now I will be, V is written as V, and Vc actually we have already proved the value of Vc. Vc is V into 1 minus e to the power minus t by R into C, right? So after by R, so after simplifying we can write V by R e to the power minus t by RC. So this is the expression of I. Okay, this is the expression of I. Okay, so now the capacitor voltage. The next thing is capacitor voltage. That is basically Vc. So the Vc will be, actually Vc is already got Vc equal to V into R minus T by RC. So okay, so we have already found Vc and I, right? So the main thing is that should be discussed, that is Vc equal to V into 1 minus T e to the power minus T by RC, right? So now if we put at t equal to 0, so at t equal to 0, this is what? At t equal to 0, Vc is equal to 0. By putting t equal to 0, you can calculate Vc equal to 0. And at t equal to tau, at t equal to tau, that means at that position Vc is equal to V into 1 minus 1 by E, by putting the value of t equal to tau in this Vc expression. This is the Vc expression. Okay, so that means it is near about to 0.632 volt. That means the 63.2% of supply voltage. That means the time taken to reach the 63.2% of the initial voltage of the capacitor at steady state is known as time constant. Clear this thing? So next, and at t equal to infinity, at t equal to infinity, by putting the value of t equal to infinity, it is almost same as Vc equal to V. So at starting the value of the capacitor voltage is 0, and at final it is the value of the supply voltage that we have already applied in our simulation, that is the 10 volt, Vc equal to V. So right, so then, so if I stage the current, current is already got, that is I equal to V by R e to the power minus T by RC. We have already proved it in our previous slide. So at t equal to 0, I is simply V by R. Okay, at t equal to tau, so tau, after putting the value of t equal to tau, I will be V by R into 1 by E, right? And at t equal to infinity, then I equal to V by R e to the power minus infinity, actually it is 1 by e to the power infinity, and I equal to 0. So these three things we have to remember during the switch on: the value of current during the switch at the starting and at the position of time constant, and at the final, the steady state. So these are the main three part. Okay, so now the last thing is voltage across the resistor. Voltage across the resistor. So what will be the voltage? VR equal to V minus Vc, and then VR equal to V minus, after putting the value of Vc, it will be V e to the power minus T by RC. So this is the expression of capacity, the voltage across the resistance VR. Okay, and similarly at t equal to 0, VR equal to V. That means the voltage across resistance is same, that is appearing on the supply voltage. Okay, and if I put t equal to infinity, so VR equal to V e to the power minus infinity, it is equal to basically 0, right? That means the voltage across from these two equations, we can we can tell that the voltage across the resistance starts from a constant value, that is the supply voltage 10 volt. Okay, uh, and finally it reaches the steady state value of the 0 volt. Okay. So the capacitors charged value V at t equal to 0, and at t equal to infinity the capacitor will fall to the 0. Okay, so this is mainly the two thing, because the capacitor voltage equation is at t equal to 0 it is 0, and at t equal to infinity it is the supply voltage, right? So this is basically the all about the transient analysis of the series RC circuit when the switch is on, and the graph sorry, and the graph will be like that. Suppose this is the axis. Okay, so first of all, this is the, suppose this is supply voltage of 10 volt. It is basically V. Okay, what is V? That is also VR. Okay, and then the voltage across resistance, it is starts from the V and finally it is 0, right? So that means if I draw it is in a blue line, that means it starts from the V and finally it will reach the 0 value. Okay, so the blue one is the V voltage across the resistance, right? And the current expression is, it starts from is at t equal to 0, it starts from V equal to t equal to V by R. That means the supply voltage is 10 volt, R is 2 ohm. That means it is basically 5 ampere. It starts from the 5 ampere and finally it reaches the value of 0 ampere. That means similarly, suppose this is a V, and if I measure this portion is more or less V by R, that is a 5 ampere. Okay, V by R. Just think is that. So if I draw the line again, it will start from V by R and fall to 0 ampere, right? And the last thing is the capacitor voltage. Capacitor voltage is, it started from the 0 volt and finally it is supply voltage V. Very simple. So if I take a different color, that means it starts from the 0 volt and finally it will reach the final value of the V, supply voltage. So VR is the voltage across resistance. Red one, the red one is, it is basically the I actually, I. Okay, the red one is I, that is equal to V by R, and the this gray color, gray one is basically the voltage across the capacitance. Okay, it starts from the 0 value and finally it reaches the steady state value of the 10 volt. So this is all about the series RC circuit when the switch is on. So now at source free condition, similar for the RL circuit, at source free condition, so this, suppose this is the supply voltage, and now the switch is suppose open. That is basically the, there is no source connected, R and C. Okay, this is the supply voltage, it is not connected here. So at switch off, what is the KVL equation? VR plus VC, that is equal to 0. Simple, because the supply voltage is irrelevant here because the switch is open, right? So VR equal to, that means 0 equal to, VR means I into R and VC is just same VC. So I equal to dq dt. So we can write 0 equal to dq dt into R plus Vc. Okay, and Q equal to again Cv. So Q equal to Cv, Q equal to CV. So dq dt is C dvc dt, right? So that is 0 equal to R C dvc dt plus Vc. Okay, so that means we can write RC dvc dt, that is equal to minus of Vc. Okay, so now by arranging this portion we can write that minus dvc by Vc, that is equal to 1 by Rc dt, and take the integration on the both side. So after simplifying the integration we can write minus ln Vc plus k equal to T by Rc. So at starting, that means at t equal to 0, the same thing, t equal to 0, that is equal to Vc equal to the capacitor voltage. Look, first of all the switch is on, the inductor current starts charging and the capacitor voltage starts to store its voltage or charge. So at t equal to 0, during the switch off, it will release its energy, that it is its charge. That means Vc starts from the supply voltage capital V. During the switch off condition at t equal to 0, it will about to discharge, but before that it starts from the supply voltage V. So Vc equal to V. So putting the value minus ln V plus k equal to T by Rc. So that is equal to 0 basically. So k equal to ln V. This is the condition. Now putting the value, we can write minus ln Vc plus k means plus ln V equal to T by R into C. So that from that ln Vc by V, that is equal to minus T by Rc. From that we can write Vc equal to V into e to the power minus T by Rc. So this is the voltage across the capacitance during the switch is off. This is a discharging voltage. Okay, and from the second KVL equation, that is basically this equation. This is number 2. Okay, we can write from 2 we can write VR plus Vc equal to 0. That means I into R equal to minus of Vc. So that means I equal to minus Vc means actually minus V e to the power minus T by Rc, right? That means I equal to just V by R minus V by R e to the power minus T by Rc. So this is the expression of current when the switch is off. That is the source. That means the source P condition. That is basically the discharging current. Okay. And next one is the voltage across the resistance. Okay. The voltage across resistance, it is basically VR equal to minus Vc. So that means VR equal to minus of V e to the power minus T by Rc. So it is the voltage across the resistance. From KVL equation it is easily can be written. Okay. So now if I put the condition at t equal to 0, at t equal to tau, and at t equal to infinity, that means starting and time constant period and the final period. So at t equal to 0, the Vc capacitor voltage equal to V e to the power minus 0 is equal to V. Okay. At t equal to tau, that is Vc equal to V e to the power minus t by tau, actually tau by tau, t equal to tau, okay, that is V e to the power minus tau by tau, that is Vc equal to V e to the power minus 1, that is 0.368 volt, okay, and at t equal to infinite, Vc is 0 volt. From the equation of Vc in case of switch off, the source free condition, okay, that means the capacitor voltage starts decreasing from the charge value of the source voltage, that is V, and finally it becomes 0. From it will start from the supply voltage V, and finally it will reach at the steady state value of 0 volt, okay. Similarly for current, at t equal to 0, at t equal to 0 the current is minus V by R, okay. If I put the expression of current, that is basically minus V by R e to the power minus t by RC, if I put t equal to 0, that is basically minus V by R, right. So at t equal to infinite, the current is V by R minus V by R into 1 by e to the power infinite, that means e to the power minus infinity, so it is 0, so I equal to 0, that means again the look, the expression for current is plus V by R when the switch is on, and when the switch is off, the expression for current is minus V by R, that means the polarity will reverse, that means the one is charging current, when the switch is on, the magnitude is minus V by R, and one is discharging current, when the switch is off, and the magnitude value is minus V by R. The minus sign denotes that one is charging and one is discharging, but the magnitude is same, okay. So next, the voltage across the resistance VR at starting t equal to 0, so it is equal at t equal to 0, VR equal to minus of V volt. Look, at t equal to 0, VR is minus V volt, okay, and at t equal to infinite, VR equal to minus V e to the power minus infinity, that is equal to actually 0 volt. So this is basically the a tabular format, what the behavior of the voltage across the resistance, voltage across the capacitance, and the current, okay. So this is the voltage across the resistance at t equal to 0 and at t equal to infinite, that means from the equation, from the equation of capacitor voltage, it is clearly written that where the source okay, it is clearly written that, look, during the switch on, it is written 63.2% of supply voltage, okay, from that equation, time taken to reach 63.2% of the steady state value, that is a 10 volt, 10 volt of 63.2%, okay. So now if I plot the graph, it is very simple. First of all, this point is the supply voltage V and the capacitor voltage. First of all, capacitor voltage at 0, it is supply voltage V, and it is infinity, it is 0, right. So that means it starts from the supply voltage V and reaches the 0 value. So Vc is the voltage across the capacitance, okay. So now VR is minus V, and similarly it is 0, that means it starts from the minus V, the polarity will reverse because one is charging, otherwise one is discharging, and it will reach the 0 volt, okay. So this is VR, right, and the expression for current is starting from minus V by R, that is more or less this portion is minus V by R. Okay, and if we take this color, and it starts from minus V by R and reaches to here. Look, it is to 0. That means at steady state it will reach the 0 value. So this is the basically current. Okay. So this is the graph of the voltage across capacitance, voltage across resistance, and the current during the switch is off. So this is all about the gist of the time domain DC time domain analysis of the series RC circuit. So now there are two important questions. The first question is, we have already got that the time constant of RC circuit, of basically C is RC circuit. It is equal to RC. That means tau is equal to RC. So now prove that the unit of time constant is equal to time in case of series RC circuit. Similar as the case of series RL circuit. So now tau is RC, R equal to V by I, C equal to Q by V, right? That means V cancelled out, Q by I, so Q equal to IT, that's so Q by I equal to T, that is the time. So the time constant of the unit of time constant is also time. Okay, it is again proved, right? The second question is, if I again go back to the expression of the capacitor voltage, so at switch on condition, the capacitor voltage is V into 1 minus e to the power minus t by RC. Okay, here we have already performed on it. So at t equal to 0, the Vc is 0. At t equal to infinity, Vc is V. So Vc is 0. The meaning of this word is the voltage across the capacitor is equal to 0. That means the capacitor is short circuit here. As the capacitor is short circuit, so the voltage across this capacitor is equal to 0. And finally, the voltage across the capacitor is appear on the same DC voltage. That means there is no potential drop across the capacitor. The same DC voltage is shown over here. That means at final stage, the capacitor is basically the open circuit. So the important note is capacitor is initially in bracket t equal to 0 short circuit, and capacitor is finally, that means t equal to infinity, it is open circuit. This is very much important for GATE exam also, for MCQ purpose. Okay, so this is basically all about the DC transient analysis of series first order RC circuit. So now if I check the same result on simulation, so what will be the simulation result? Look, so this is the circuit of series RC circuit. Here same supply voltage is 10 volt, R is again 2 ohm, and C is basically here 2200 microfarad, and we set the capacitor initial voltage is 0 volt, right? So if I run the simulation, I think it is done. The first one is supply voltage, second one is current, third one is voltage across the resistance, and the fourth one is the voltage across the capacitance. Okay, so this is appearing in the graph. So first one is the DC voltage, second one is the current. So current is start from the 5 ampere, that is V by R at initial stage, and finally it reaches the zero value. Third one is the voltage across resistance. It is basically V by, that means the V supply voltage 10. It starts from the 10 volt initially and finally it will go to the 0 volt. Last one is voltage across the capacitance. It starts from the 0 value and finally it reaches the steady state value of 10 volt. Just cross check it in case of switch on. In case of switch on, the graph will like that. V, the voltage across resistance, and the current is decreasing, but the capacitor voltage is increasing, starts from the 0 value and reaches the final value of supply voltage 10 volt. So now the capacitor voltage, okay, the time constant of RC circuit is R into C. That means R here 2 ohm, C is 2200, that means 4400 almost. That means so 4 millisecond we get the value of 4.4 millisecond we get the value of the capacitor voltage, 63.2% of the capacitor voltage. So capacitor voltage is 10 volt, which 63.2% means 6.32 volt, right? The capacitor voltage finally the steady state value is 10 volt. The 63.2% of the steady state value, that means 6.62 into 10, that is 6.32 volt when at the time of 4.4 millisecond. So if I zoom that portion, this is 5 millisecond. So before slightly left, that portion is 4 millisecond. So in 4.4 millisecond, it will reach the value of, if I zoom this section, if I zoom this section, so at 4.4 milliseconds, suppose this is the portion, it will reaches 6.32 volt. So just crosses the line of 6 volt, it is almost 6.32 volt. So now from the graph it is also clear the concept of time constant. So this is actually very easy, nothing is complicated in that. Okay. So so basically this is all about the DC time domain analysis of the first order series RC circuit.